Now, continuing on with the topic of testing the null hypothesis that the covariance matrix is a diagonal matrix against the alternative that it's not a diagonal matrix. In other words, we're testing the null hypothesis that none of the variables, response variables, are correlated with each other against the alternative that at least two of the variables have a non-zero correlation. And so we looked at the development of this type of test. It's a likelihood ratio test. And so what I want to do now is look at an additional example from the website. And so here is the course website, and I'm going to follow the link, Programs and Solutions for selected examples and exercises. And in this video, we're going to look at an analysis of one of the data sets from the Brian Manley text. In particular, we're going to again look at this data involving the body measurements of female sparrows, which we looked at in a previous lecture video. Now remember, the data set contains 5 measurements on various characteristics of birds that had been injured during a storm back in 1898 and had been taken to the lab of Herman Bumpus. And so we have these 5 response variables, x1 through x5. x1 is the total length of the bird. x2 is the alar extent, which is the distance between the tips of the wings fully extended. x3 is the length of the beak and head. x4 is the length of the humerus. And then x5 is the length of the keel of the sternum, which is shown here in blue. It's the ridge along the breastbone of a bird, and it's that's where the flight muscles are attached. Now, when we originally looked at this data set, we were looking at this in the context of doing a principal component analysis. And you'll remember that the primary purpose or objective of a principal component analysis is to determine the true dimensionality of a data set for the purpose of seeing if we can reduce the dimensionality by looking at a smaller number of indices computed from the original variables. Now, in this data set, again, has 5 response variables, x1 through x5, and we'll look at a listing here of those data. And so the dimensionality of the continuous responses in this data set is 5. All right, so the data can vary throughout 5-dimensional Euclidean space in this situation. But if the data do not vary throughout all 5 dimensions, then we can perhaps reduce the dimensionality by looking at these indices which are constructed from the original variables. And you'll remember that that's what we looked at in the context of principal component analysis, and we determined that we could get by with using 1 or at most 2 of the principal components because the first principal component accounts for 86.22% of the original variability, or the total variability in the original variables. And if we were to use the first 2 principal components, then those 2 principal components together would account for 97.51% of the total variability in the original variables. And so what this is telling us is that although the data is 5-dimensional, it's not varying throughout all 5 dimensions. It's really only varying in primarily 2 dimensions. And so that allows us then to reduce the dimensionality of what we're looking at with respect to this data by focusing on these 2 indices, the first 2 principal components, which again are computed from all 5 of the original variables. Now, situations where a data set may not be varying throughout all p dimensions available to it are when there is correlation among the original variables. If none of the variables in a data set are correlated with each other, In other words, if the population covariance matrix for that set of variables is diagonal, then that data is going to tend to vary throughout all dimensions available to it. But if there are correlations among variables, and if those correlations are somewhat strong, either positive correlations or negative correlations, then that's going to be a situation where the data may not be varying throughout all of the p dimensions available to it. And so it's useful to be able to determine whether any of the variables are correlated with each other. Now, with that in mind, when we first looked at this data set, prior to doing the principal component analysis, we looked at scatter plots, pairwise scatter plots of the variables, as well as a correlation analysis. And so when we looked at a scatter plot matrix of the variables, we saw that it appeared to be fairly strong positive linear relationships between the pairs of all of the response variables. In other words, it appeared that there were positive correlations between each pair of response variables. And in following up with that from a numeric standpoint, we looked at the output of PROC-Core, which does correlation analyses. And in particular, we looked at this estimated correlation matrix. And if you look at the entries in this correlation matrix, in fact, let me blow that up so we can see a little better. So the estimated correlation between x1, the total length, and x2, the Alor extent, is fairly strong, 0.73496. And this value here in the second row, or the second entry in that cell, which says less than 0.0001, this is the p-value for the null hypothesis that the population correlation between x1 and x2 is 0. Okay? And because that p-value is very small, for example, we could test this hypothesis at the 0.05 level of significance. Again, testing the null hypothesis that the population correlation between x1 and x2 is 0, indicating no linear relationship between the two variables, against the alternative that the correlation between x1 and x2 is non-zero, so that would indicate that there is some level of a linear correlation, or I'm sorry, a linear relationship between the two variables. The p-value for this test, again, is less than 0.0001. Now, remember how we use p-values in testing hypotheses. If the p-value for a test is less than or equal to the significance level that we choose to use, then our conclusion is to reject the null hypothesis and conclude that the alternative is true. And so in this case, if we are using a 0.05 level of significance, then because the p-value, which we know to be less than 0.0001, that would imply then that it's also less than or equal to 0.05. Specifically, it's less than 0.05, but the criterion is if it's less than or equal. So for this first test, we would reject the null hypothesis of no correlation, of 0 correlation between x1 and x2, and conclude that the population correlation between x1 and x2 is different than 0. Likewise, looking at this cell here for x1 and x3, the estimated correlation between x1 and x3, based on the data, is 0.66181. Now, that is non-zero, and it's fairly large, but the question is it big enough to lead us to conclude that the population correlation between x1 and x3 is non-zero? Well, to answer that, again, we perform the hypothesis test, and again, if we're going to use a 0.05 level of significance, we would conclude that the null hypothesis is false, and therefore that the population correlation between x1 and x3 is non-zero, because this p-value, again, the p-value for this test is less than 0.0001. And we could continue on and draw that same kind of conclusion for the population correlation between x1 and x4, x1 and x5, x2 and x3, x2 and x4, x2 and x5, x3 and x4, x3 and x5, and x4 and x5. Now that's a lot to talk about, that's a lot to say, isn't it? Well, that's because there are a lot of correlations. Pairwise, when we consider 5 variables, there are 10 different hypotheses. There are 10 correlations that we're talking about between the variables, and therefore 10 hypothesis tests. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 tests. Okay, when we have p response variables, then the number of correlations between pairs of variables is equal to p times p minus 1 over 2. And so with 5 variables, the number of correlations, and therefore the number of tests, individual tests, is 5 times 4 over 2. All right, and so that's 10. Now, every time we do an hypothesis test, there is the potential for committing a type 1 error. So, even though we've rejected, because we've rejected the null hypothesis, we really don't know for sure whether the null hypothesis is true or not. We're concluding, in this first case here, we're concluding that the null hypothesis is not true, and therefore that the population correlation between x1 and x2 is different than 0, but we don't know with a certainty. There is the possibility that because of the data we've been led astray, we've come to the wrong conclusion, all right, and in that case that would be a type 1 error. Remember that a type 1 error is when you reject the null hypothesis when in fact the null hypothesis is true. But now the way that we've set this test up is that the probability of our committing a type 1 error is only equal to 0.05, which is the significance level that we used for the test. Remember, that is the definition of the significance level. It's the probability of rejecting the null hypothesis when the null hypothesis is true. So we performed each of these 10 different hypothesis tests at a 0.05 level of significance. Individually, each of these tests has a significance level of 5%, 0.05. In other words, for each test, the probability that we conclude that the null hypothesis is true when it is actually true is only 0.05. However, if we think of these 10 tests collectively, all together, what is the probability that we conclude that at least one of these null hypotheses is false when in fact all of the null hypotheses are true? In other words, if none of these 5 variables are pairwise correlated with each other, what is the probability that we will conclude that at least one of these pairs is positive, or has a non-zero correlation? Well, that probability, which we call the overall type 1 error rate, or in this, we also call it the experiment-wise error rate, at least as it pertains to testing hypotheses about these correlations. This overall type 1 error rate is not 5%. It's going to be something bigger than 5%, and it could be something actually, quite a bit larger than 5%. And the magnitude, or how big this overall type 1 error rate can be, increases pretty quickly as the number of response variables increases. So if you'll remember, when we looked at this data set before in a previous lecture, and we in particular looked at this correlation analysis, we said that we would not want to draw conclusions about whether or not the variables were correlated with each other based on this correlation, this correlation analysis all by itself, because this correlation analysis all in and of itself does not do anything to control for the overall type 1 error rate. And so we would want to use some other kind of a procedure along with this. And that's what we're doing when we test this hypothesis that the covariance matrix is a diagonal matrix. Because that test is specifically testing the null hypothesis that all of these population correlations, all 10 of these correlations are zero against the alternative that at least one of them is non-zero. So it allows us to perform all 10 tests in this case, and in general, all p times p minus 1 over 2 tests at a specified significance level, for example, 5%. So while these individual tests could be done at a 5% significance level individually, we can perform all 10 tests simultaneously at a significance level of 5% using this procedure that we're looking at currently. And so then what the process would be, we first, in trying to determine whether any of the variables are correlated with each other, we would first perform this overall test, which is the test we're looking at right now. And then if we reject, and remember that the null hypothesis for that overall test is that none of the variables are correlated with each other. If we reject that null hypothesis at a significance level of alpha, then what we would do is, well, number one, we would conclude that at least one pair of variables has a non-zero correlation. And then as a follow-up, if it were important for the purpose of the analyses, the subsequent analyses, if we needed more information about which variables were correlated, then that would be the time that we would drill down into the body of this table containing these individual tests and then see which one of these are different from zero based on their p-values. And so if we do the overall test at a significance level of alpha and we reject that, then we could come in here and do each of these tests at the same significance level of alpha. And so I told you when we first looked at this correlation analysis that at some point in the near future we would come back and revisit this data set and revisit this example, and we would perform that kind of a test. And so that's what we're going to do now. We're going to perform this overall test where the null hypothesis is that all of the 10 correlations corresponding to correlations between the pairs of variables, all of these correlations are zero against the alternative that at least one of them is not zero. And so let's go back here and let me just show you. If you look here under the same set of analyses, I have some analyses here. Analyses for testing the hypothesis of no correlation between the original variables. And we have two analyses, and you'll see that we get the same results for both. The first analysis is based on the sample covariance matrix. Remember that that is the unbiased estimator of the true correlation, or the true covariance matrix. And the second analysis is based on the MLE, the maximum likelihood estimator of the covariance matrix, which is, you'll remember when we talked about, in that section on estimating the parameters of the multivariate normal distribution, that is a slightly biased estimator of the true correlation matrix. Now we have both of these analyses because technically the likelihood ratio test, which is the test that we are using, calls for using the MLE of the covariance matrix, or if we're analyzing the standardized variables, analyzing the MLE of the correlation matrix of those variables. But what we're going to find is that because the sample covariance matrix is just a scalar multiple of the MLE of the covariance matrix, that particular adjustment that takes it from the MLE to an unbiased estimator of the true covariance matrix. In other words, that scalar multiple takes it from the MLE to what we call the sample covariance matrix. That multiplicative factor cancels out in the calculation of the test statistic, and so that is why we can actually use the information provided in the principal component analysis in order to calculate the value of the test statistic. And so let's talk briefly about how to go about doing this test. You'll remember that the null hypothesis is that the covariance matrix for the variables, the population correlation covariance matrix is a diagonal matrix against the alternative that that covariance matrix is not a diagonal matrix, that at least one of the off-diagonal elements is non-zero. Okay, and then we can use either of these two formulas, and we then compare the value of the test statistic, whichever one we choose to use, to the upper alpha percentage point of a chi-square distribution with degrees of freedom equal to p times p minus 1 all over 2. Okay, so that's the procedure. And again, we need to determine these lambda hats as well as these sigma hats in order to calculate the test statistic. And those values, as I stated and as we looked at in the previous lecture video, those values are given as output from proc.princom. And so, for example, if we were to look at the output from this principal component analysis here, and by the way, what I'm going to do right now is to use the, because the variables are all measured with the same units, right? These are all lengths. Let me go back here. These are all lengths, and they're all measured in millimeters. They have the same unit of measurement. I'm going to analyze the original variables rather than the standardized variables. The variables are on an equal footing, which would really not be the case if they were measured in different units. But because they are measured in the same units, the data, the variables are on the same footing, and so it's reasonable to perform the principal component analysis on the unstandardized variables. And so if we look at the output from this principal component analysis, where are the values that we need to to calculate the test statistic in performing this hypothesis test? Well, again, what we need here, going back here, we need the lambda hats. Those lambda hats are given as the eigenvalues or characteristic values of the estimated covariance matrix. So the 35.325759, the 4.6224593, and so forth. And again, what we have to do is we have to multiply those together. We also need the sigma hats. Now, where are the sigma hats? Those are the diagonal elements in the estimated covariance matrix. So 13.35374150, 25.68282313, and so forth. So we would multiply those values together, all right, and that product would go in the denominator. We calculate the ratio of those products and then calculate, again, the natural log. This is not log base 10, this is the natural log, okay? And then once we have done that, then we multiply that by negative n, where n is the sample size. So we see here that we can get the values we need from the output from proc.princom, which is the principal component analysis that as we do it in SAS. Now, we could also, if we wanted to, instead of having to do the principal component analysis and identifying these values and plugging them into a calculator by hand, we could also write a program to extract the characteristic roots and the estimated variances. And that is what I've done here using proc.iml. And so you saw the similar kind of analysis that we did in the previous example using proc.iml to calculate the values of the test statistics and carry out the hypothesis test. And so here I'm using proc.iml to summarize the data. I've got 49 observations. There were 49 birds. There are 5 response variables. The estimated mean vector is given by this vector I'm calling x bar. The estimated covariance matrix, which I'm calling cov, is given here. If you go back to the output from proc.princom, you'll see that these are the sample means, And these values, rounded to 3 decimal places, are the same as the values in the estimated covariance matrix given by Proc-Princom. The characteristic roots of this estimated covariance matrix are given here. So 35.326, 4.622. And let me just also point out that these values are being displayed to rounded to 3 decimal places, but internally PROC-IML is keeping the full precision of these values, which is double precision. All right, so it's retaining that precision even though it's only displaying these values to rounded to 3 decimal places. So again, what we need to calculate the test statistic, we need the lambda hats. These are computed from the estimated covariance matrix where we're not imposing any restrictions on the estimation procedure, and those are given by these characteristic roots. These are the characteristic roots of this estimated covariance matrix. The other quantities we need, the sigma hats. Remember that the sigma hats are the estimates of the diagonal entries of cap sig estimated over the subset of the sample space that is represented by the null hypothesis. Okay? In other words, and so in this case, these sigma hats would be estimated from the estimate of the covariance matrix that is computed or determined under the condition that the covariance matrix is a diagonal matrix. And I've got that estimated covariance matrix here. I'm calling that cov_HO. So this is the estimated covariance matrix under the condition of the null hypothesis. So note that all of the off-diagonal elements here are 0. The only non-zero values are the estimated variances on the diagonal. Now, in the previous lecture video, I told you that it turns out that the estimated variances, the estimated variances in that covariance matrix computed under the condition of the null hypothesis are the same as the estimated variances in the estimated covariance matrix when we are not restricting the estimation procedure to the null hypothesis. And so to demonstrate this, I just want you to look. Notice that these diagonal entries up in this general sample covariance matrix, 13.354, that's the same value we've got down here. 25.683, the same value we have down here. The diagonal entries in this matrix are the same as the diagonal entries in the matrix that the procedure actually calls for. And so that is why, and that will always be the case, and that is why we can use those values from the output of Proc-Princom, even though technically it's not imposing the constraint of the null hypothesis on estimating those variances. All right, so having said that, and been more specific about that now that we can look at this Proc-IML output, then after that we have the calculations for calculating the value of the test statistic. And so remember that in this formulation for the test statistic, the way it's written here, it's minus n times the natural log of this ratio. But using properties of logarithms, the log of this ratio is equal to the difference between the natural log of the numerator and the natural log of the denominator. So in other words, the log of this product minus the log of the product in the denominator. And that is that's how I'm going to calculate this in the context of Proc-IML. And so this value here, 0.916, this is the log of the characteristic roots. I'm sorry, it's the log of the product of the characteristic roots. Okay, and so let me go back up here. Here are the characteristic roots. What I've done is I've taken the product of these characteristic roots, and then I've taken the natural log of those values, and that the natural log of the product of those characteristic roots is 0.916. Then I'm going to calculate the natural log of the product of the estimated variances. Okay, and so I'm going to calculate the product of these estimated variances and then take their log, natural log. And when I do that, I get 4.216. Now, then what I do is I take the difference between 0.916 and 4.216, and then I multiply that difference by negative n. Now remember that n is 49. Okay? And so if we do that, if we take 0.916, subtract 4.216, we get negative 3.3. Then multiply that by negative 49, and we get 161.7. Now, the output from PROC-IML gives us something slightly different, 161.75, and that's because, remember that PROC-IML is retaining all the full precision of all these values. So even though we're rounding it here to 0.916, PROC-IML is retaining the full precision of what that natural log actually is. And the same for this natural log of the product of the variances. And so what we're seeing here, the difference between the 161.7 and the 161.75 is just the difference that occurs because we've introduced rounding in each of these, and so that rounding error propagates to this final answer. Okay, it's not going to make a difference, obviously, but I just wanted to point that out. So it's not going to make a difference in this particular situation. Now, if you have calculations where you are rounding and you've got many calculations and you have to round many values, then you're going to be propagating more and more error, and that can really throw you off. So I always recommend that you retain the full precision of all the values in your calculations that is possible by doing all the calculations in the calculator itself and then rounding only at the final result. So the test statistic, the first form of the test statistic for this test is 161.75. If we use the second formula, then the second form of the test statistic is 150.19. As is always the case, the second version of the test statistic is going to be somewhat smaller than the first. That's the whole purpose. And that tends to give that second test statistic a slightly better overall type 1 error rate. But we're not going to worry about that right now. Okay, so then this test, because there are 5 response variables, the number of degrees of freedom associated with the test are 5 times 4 over 2, or 10. So this is a 10 degree of freedom chi-square test. If we are going to use, let's say, a 0.05 level of significance, then the critical point obtained from the chi-square table is 18.307. And so the rejection criterion is to reject the null hypothesis if the test statistic that we're using is greater than the critical point 18.307. And you can see that, regardless of which of these test statistics we use, they're each greater than 18.307, and in fact they're a lot larger, and in fact almost 10 times larger, 8 to 10 times larger than the critical point. And so there is very, very strong evidence that at least one pair of the response variables is correlated. Okay, at least one pair of the response variables has a non-zero correlation. And so we can test the null hypothesis that all 10 of these correlations are zero against the alternative that at least one of the correlations is non-zero. And that test, that null hypothesis is rejected. There's very strong evidence that at least one pair of variables has a non-zero correlation. And so now, and let me just back up and say that the overall type 1 error rate for that test is 5%. So we're protected at with a significance level of 5%. Now we can, if we so choose, we can look at these individual tests and decide which pairs of variables are correlated. And in fact, we could now conclude, based on these p-values, that all 10 pairs of variables have non-zero correlation. And we can, by virtue of using these two tests together, the overall test, the first test, okay, based on this overall or omnibus test, which simultaneously tests the null hypothesis that all 10 correlations are zero, against the alternative that at least one of the correlations is non-zero, we can, that in conjunction with the 10 individual tests in the output from PROC-Core, we can conclude, therefore, that all 10 of these correlations are non-zero, and the overall type 1 error rate that we have for this combined procedure is 5%. So that is that's another example of showing how we can perform this overall or this omnibus test involving all of the correlations between the response variables to check to see whether any pair of variables has a non-zero correlation. And because of that, because we can conclude that, and we would probably do this before we would even do the principal component analysis, or at least before we would focus on the results of the principal component analysis, it would then make sense to at least to have an expectation that we could reduce the dimensionality of the data set from 5 to something smaller than that, because we see that these variables are so highly correlated with each other, that all pair of variables are correlated, and so we would expect then that we would be able to reduce the dimensionality of the problem. So that is all I'm going to say in this lecture video. Again, it's an example of this likelihood ratio test, where we're testing the null hypothesis that the population covariance matrix is zero against the alternative that it's non-zero. I'm sorry, not the zero. The overall, I misstated that. I'm sorry about that. Testing the overall, the null hypothesis that the population covariance matrix is a diagonal matrix against the alternative that it's not a diagonal matrix. So just wanted to be clear on that.